Hello everyone. So in the previous lecture we discussed different categories of quadratic forms. Now today we shall see what can be done with a positively finite matrix which is symmetric in nature. So here comes the result which is properly known as Cholesky decomposition or Cholesky factorization theorem. So the result goes like this. Let let A be a symmetric matrix with which is also positively finite and the order of the matrix is n, then there exists a lower triangular matrix T such that A can be written as T into T transpose. So the result will hold true if we can find a way to calculate this lower triangular matrix T, assuming that the matrix A is symmetric positively finite matrix. So let us take this matrix T. Let T11 0, 0 onwards would be then the first row, T21, T22 and then 0 onwards would be the second row and so on. So the matrix T being lower triangular matrix, all these elements in the upper triangle of the matrix T will be zeros. So the last row will be Tn1, Tn2 up to Tnn. So the last row will not contain any zeros. So let us see how then T prime will look. So if we consider T like this, then T prime will be, T will be here and T prime will, now rows will become columns and so it will look like this. So if we multiply this T with T prime, what do we get is, the first will be T11 zeros into T11 0 plus 0 into 0 plus 0 into 0 and so on. So the first element of the first row of the product of matrices T and T prime will be simply T11 square. Then the second element. The second element in the first row will be multiplication of the first row and the second column. So first row when multiplied with the second column, the second element all onwards need not be taken into account because here all are zeros. So T11 into T21 that would be the second element in the first row of the product. Similarly, T11 into T31 would be the third element in the first row of the product and so on. The last element in the first row would be T11 into Tn1, this element, this term. Now let us consider the second row. The second row would be T21 into T11 plus T22 square. Sorry, let us consider the first element in the second row again. So it will be T21 into T11 and the next elements in the first column are all zeros. So nothing will come out of it. And so the first element in the second row would be simply T21 into T11 square. Now let us consider the second element in the second row. So that would be product of second row and second column. So it would be T21 T21 into T21. So that would be T21 square plus T22 into T22. That would be T22 square. Now here onwards these elements will be zeros. So the second column will have the third, from the third element onwards, the second column of T prime will contain only zeros. And so as a result, the second row of T prime will contain only two terms from the second term onwards. So this third term in the second row would be T21 into T31 plus T22 into T32 and so on. So the last element in the second row would be T21 into Tn1 plus T22 into Tn2. Similarly, the third row would be T31 into T11, T31 into T21 plus T32 into T22. Then from third element onwards, there would be each term will contain addition of three terms. So T31 square plus T32 square plus T33 square, that would be the third term and so on. Lastly, the last term in the third row would be T31 into Tn1 plus T32 into Tn2 plus T33 into Tn3 and so on. So finally, the last row would be Tn1 into T11, Tn1 into T21 plus Tn2 into T22. So the first element in the last row will have only one term. Second element in the last row will have two terms. Third element in the last row will have these three terms and so on. And lastly, the last element in the last row, that is the nth element would have n terms. So addition of n terms. So that would be Tn1 square plus Tn2 square and so on up to finally it will be Tnn square. So this is how T into T prime will look like. So now we have to equate the matrix A with this T prime. So if we visualize the matrix A like this, where first element is A11, second is A12 and so on, then what we can do is now we can try to identify the elements of matrix A. So let us start with the first row and we shall go from left to right. So what we will do is we will equate A11 with T11 square. So the first row will give us A11 equal to T11 square. Then A12 will be equal to T11 into T21. Now see, we have got, so T11, we will have T11 as square root of A11. So this T11 we can substitute here and we get A21 equal to square root of A11 into T21. Similarly, we can equate A13 to T11 into T31. Now T11 we already know. So we can calculate T31 also. Likewise, now the last element in the first row would be A1n equal to T11 into Tn1. Here T11 is already known. So Tn1 we will go get by equating A1n equal by writing A1n equal to root A11 into Tn1. So we can take this root to this side and we can get the expression of the first row of matrix T by solving these equations like this. So T11 is plus minus root A11, T21 is A21 upon T11 and so on. So because we can take either plus or minus root, this Cholesky factorization is not unique. So it is still possible to have minus root of A11 or plus root of A11 and still it will be true. But by default, most of the textbooks, they consider only positive root and so we can ignore the negative roots here. So similarly, if we equate the elements of the second row, we get T21 as A21 upon T11, T22 square as A22 minus A21 upon T11 whole square. So this will give us A22, T22 like this and so on. So we go on doing this for each element of the second row and we get entire second row of matrix T. Similarly, if we equate elements from the third row, we get third row of the matrix T like this. And finally, continuing like this, we get lastly the last element of the matrix T as a root of ANN minus TN1 square minus TN2 square and so on up to minus TNN minus 1 square. Now here is the remark which I have already made because square roots involve two roots, so positive or negative. But by default, please remember that by default, most of the cases, positive square root is considered. So the standard procedure is to make the diagonal elements positive. So if we take this matrix F and if we try to diagonalize it, then by applying above procedure, we will get matrix T like this. Let us continue our discussion. So we saw how a positive definite matrix can be reduced to triangular form. Not exactly reduced, but a positive definite matrix can be written as a product of lower triangular matrix multiplied by its transpose. So let us talk more about positive definite matrices. So these are the specialities of positive definite matrices, that all characteristic roots means eigenvalues of positive definite matrix are positive. Then a positive definite matrix is always a full rank matrix. In other words, if a matrix is not a full rank matrix, then it cannot be positive definite. Then a positive definite matrix is a non-singular matrix with positive determinant. So all these three things are important features of positive definite matrices. So similar to positive definite, what can we say about non-negative definite matrix? So suppose A and B are non-negative definite matrices, then can we show that diagonal of AB, means if we put A and B like this and put rest of the elements as zeros in a matrix, then will it be a non-negative definite matrix? And if both A and B are positive definite, sorry, if A is positive definite and B is negatively finite, then what can we say about such a matrix C? So let us see what do we get. So let us take matrix C as diagonal of matrices A and B. So matrix A is say M by M matrix and matrix B is say N by N. Then what will happen is this will have M rows and this will have N rows. So this will be a 0 of order M cross N, this will be a 0 of order N cross N. Likewise. So in short, again you can create matrix C as a square matrix by putting A and B like this, and the rest of the elements are to be put as zeros. So without losing generality, we are assuming that matrix A is of dimension M by M and matrix B is of dimension N by N. So because they are, so let us first assume that both are non-negatively finite matrices. Then x prime ax will be greater than or equal to 0 for every x in Rm. So there is a mistake here. This should be Rm because A is assumed to be an M cross M matrix. So uh, this we get by following the definition of non-negatively finite matrices. Similarly, for matrix B, x prime bx will be greater than or equal to 0 for every x in Rn. So let us now consider x prime cx. What we want to show is that this matrix C is again a non-negatively finite matrix. So let us consider x prime cx. So now here this x should be of dimension m plus n cross 1. This x should be a vector from m plus n dimensional Euclidean space. So we have expanded x like this. Then we rewrite A and B like this. So capital A has elements as such as A11 to A1M and A1N to AMM. A1M to AMM. So this is matrix A and this is matrix B. Then this is the vector x. So what do we get? So we expand it. So the first row becomes x1 into a11 plus x2 into a22 up to xm into am1. This would be and the rest of the elements are zeros. So it won't contribute to the first term. So this will be the first element. Notice that this product of this vector and this matrix would be a row vector of dimension m plus n. So the first element in this row vector will be addition of these m terms. The second element in the row vector would be addition of these m terms and so on. And lastly, the last element in this row vector will be addition of these terms. So the first term would be xm plus 1 into b1n plus and so on. Lastly, it would be xm plus n into bnn. And now we will multiply this row vector by this column vector. So what do we get? So we get x1 square a11 plus x1 x2 a21 and so on plus x1 xm am1. That would be multiplying x1 with the first element in this row. Then we will multiply second element of this column, that is x2, with the second element in this row vector. So I will get x1 x2 a12 plus x2 square a22 plus so on up to x2 xm am2 and so on. Lastly, these will be the elements. So the last row will have xm plus 1 b1n plus xm plus n into xm plus 2 b2n and so on, and lastly it will be xm plus n square bnn. So notice that this entire stuff, these first, starting from this first term to the mth term, these can be treated as a quadratic form x1 transpose a x1 and the addition of the remaining n terms can be treated as a quadratic form x2 prime b x2, where x1 you can say as x1 is a vector of m dimensions and x2 is a vector of n dimensions, where this vector x1 will contain only these many elements. The elements which are involved, that is first m elements of this vector, of this column vector, will be called as x1, and the remaining elements of the vector x will be called as x2. Then the first addition of first m terms we are writing as x1 prime a x1, and the addition of the remaining n terms we are calling as x2 prime b x2. So since now this x1 itself would be in m-dimensional Euclidean space and x2 would be in n-dimensional Euclidean space. So and because a and b are non-negative definite, so we have this even for these x1 and x2. And so as a result we have both greater than or equal to 0 will mean the addition is also greater than or equal to 0. And because this is true for every x1 in Rn and every x2 in Rn, it is true for every x in m plus n dimensional Euclidean space, which makes C as a non-negative definite matrix. Now the question is the second one. Can we prove this? Can we prove or disprove this if we take A as a positive definite matrix and B as a negative definite matrix? That question is of interest. So let us, and further one more question which can be raised is why above result cannot be extended to positive definite matrices. This result has been extended, this result is holding for non-negative definite matrices. The question that arises is, can we extend the result for positive definite matrices? The answer seems to be no. Then the further question arises is why the answer is no. Now let us try to prove the second part of the result. It says that if A is positive definite and B is negative definite, then I will have this x1 prime A x1 greater than 0 for every x1 not equal to 0 and x2 prime B x2 less than 0 for every x2 not equal to 0. So when I take the addition x prime Cx is addition of the two, then it will belong to the real line, and so x prime, this makes x prime Cx as indefinite quadratic form because it is neither negative nor positive. So, this is how we prove this result. Now let us move to the next result. If A is a non-negative definite matrix of order n and P is m cross n matrix, then show that P transpose is non-negative definite. Then also deduce further that P transpose is non-negative definite for any matrix P. So let us see how do we prove this. So we have x prime ax as greater than or equal to 0 for every x in Rn because A is a non-negative definite matrix. Now let us call C as P transpose where P is a m cross n matrix. Then x prime Cx becomes x prime P prime x. Now this P prime we further split as x prime P A P prime x. Now this x prime P can be viewed as P prime x transpose A P prime x. Now let us call this P prime x as y. Then because P is any m cross n matrix, P prime x is any n-dimensional vector. So this vector y is any n-dimensional vector in the Euclidean space. So this quadratic form x prime Cx becomes y prime Ay. Now because y is also in n-dimensional Euclidean space and A being non-negative definite, this will be greater than or equal to 0. So we have shown that x prime Cx is greater than or equal to 0 for every x in Rn, and as a result we can conclude that C is also a non-negative definite matrix. So if we take this capital A matrix to be identity matrix, we get the result that PP transpose is non-negative definite matrix. No matter what kind of matrix P is, PP transpose will always be a non-negative definite matrix. Remember this result, this is an important result. Now let us move to something which is similar to this. So earlier we had taken P prime x. Now we are putting a condition on this matrix P. We are assuming that P is a non-singular matrix. Suppose P is a non-singular matrix, then we can create a transformation. So what we are doing is we are taking inverse of this matrix P and now we are multiplying it by a vector x. So we define it as y. So y is P inverse x, or you can, other way you can write x as P times y. So why we are considering this? So far we have considered quadratic forms in vector x. What if we make a transformation from x to y, where this is an, you can say, non-singular transformation. In the sense the transformation can be written as a product of a matrix multiplied by the original vector. So the original vector is x and now the new vector is y, and further we can write y as p inverse x, or we can write x as p times y. So if that is the case, then what happens to the uh, quadratic form which appears in the new vector, that is vector y. So then let us consider x prime ax. Then x prime ax I can write as py transpose a py. So I can write y prime p prime a py. So this becomes y prime by, where I am calling capital B as p prime ap. Now, so we have x prime ax. This quadratic form is transferred to a new quadratic form in vector y, where y is p inverse x. So, and the matrix A is now replaced by matrix B for the new vector. So, what can we say about this? What is the relationship between this matrix A and B? So, note that this P prime AP is matrix B. So, if we take the transpose of B, we get P prime AP transpose, which is P prime AP again, which is matrix B. So, we can say that this matrix B is symmetric matrix. Also, there is a one thing which we can quickly note, and that is if x is not equal to 0, then p times y will also, then p times y equal to 0 will happen only when y is not equal to 0. So, if x prime x is greater than 0 for every x not equal to 0, it will be equivalent to saying that y prime by is greater than 0 for every y not equal to 0. And so, we can safely say that if A is positively finite matrix, then B is also positively finite matrix in this context. Similarly, we can argue for the other categories of definiteness of matrices or quadratic forms. And so, such a matrix A and B, such matrices A and B are called congruent matrices. So, in general, congruent matrices are those matrices for which the category of definiteness is the same.